questions. I mentally prepared myself. Like
Yeah.
I know a little bit about system engineering now.
Uh-huh.
And then they're just like, "Do you want to come on base?" And like
Huh.
I paused because I'm like, "Wait." And I was like, "Yes." And they're
Uh-huh.
like, "Oh, okay, we'll organize it." And I'm like, "Oh,
That's great.
let's go."
That's great.
So possibly might go on base in a few months.
Like what bait? Vandenberg?
By Ridgecrest. So middle
Oh,
of
that's
the
right.
desert, middle
Okay,
of nowhere.
okay. Yeah, yeah.
Middle of nowhere where they test energetics.
I'm thinking of the launch base, Vandenberg up near yeah,
Oregon?
Oxnard.
Oxnard.
Yeah.
Yeah. Okay. No, I know which base you're talking about.
Yeah.
I think I might be able to tour it.
Okay.
I'm technically going in as an intern, but a full paid intern.
Yeah.
And it's basically they give you 3 tours on 3 different bases. See which one you like the most
Okay.
and which one's vibe with you. Because to get even into the progress, you have to get clearance. So
I
at that point, they're just like, yeah, you know what? If this one doesn't work for you, there's one that might.
Okay. That's awesome.
So hopefully you get clearance.
That's great.
We also discussed how, oh wait, we go. No, I was gonna say we discussed how 5-year-olds are basically cue balls in soccer. Like how whenever they go try to get for the ball, they usually just bump into each other and then they fall. That was really. You never thought about that? That is pretty. Think about it now. It's very true. If you ask the question, I will.
All right, what's up, Pat?
For optimization,
Yeah.
homework or homework for 3D.
Yeah.
You're looking at MATLAB, for example, or like a code on the canvas.
There's not. So that one's kind of a yeah, that one's kind of a made up problem. Let's talk after. Let's talk after that. Let's have to, yeah. It's a little bit of a longer explanation. So yeah.
Oh, okay. I was thinking kind of- I don't think they broke it, but they spread it. It was very. My colorblind is like this yellow. Like, what? Oh, there you go. Yeah, because you also had the same exact reaction. It was like, pretty sure I think that's just what I am. So, I just wanted to do everything else before I would need to go into that. Because everything's. Oh yeah, just overall. I didn't measure bridges. I always looked at just looked at my mesh. So I was like, yeah, I know I'm gonna use measure agents for this game. I'm gonna have to route because so many for like shapes like I was like X because they skew. No, but that's a benefit. Yeah, and then it's good, good. Then is this how you want the configuration to show?
So these are your boundaries.
Yeah,
Yeah.
because it's gonna be placed. My scenario is a bank. You just happen to be unfortunate enough to be depositing a check when a bank robbery is about to take place.
Yeah.
One scenario is that you're standing by the door and you're just able to pull it, and the other ones they told you to lay down.
Yeah.
So you're from the floor and you're happen to be next to the door, you're able to push it in.
Okay.
So that's why it makes it.
Yeah. Oh, good. Yeah, that's I want to be able to see this. Yeah, where the constraints are being applied and the magnitude. Right. Okay. Good.
So that's or aluminum panel. Next scenario. And the one thing, so do a change of material to steel. So the first boundary, that's all you request it.
Or for the figures, yes, but, just like I was talking about, that big part of this is explained too. And so basically what I'm trying to get at, from the explanation, is kind of understand the book. So as long as you can, and some of it maybe repetitive, that's okay, but as long as you can describe what's going on. Maybe some concern areas on, so, one thing, sometimes I tell people that you have areas where it's not right, a little bit here, like, what kind of your interpretation of water? Or just anything. So high stress usually is a high depth, usually interesting, kind of explain how why that shows me that you're analyzing.
Right, but I did mention, like, but it's slightly below and also that they have higher stress in these two things versus. Yeah, because not.
Yeah, not good. And one other thing I would say is that, because these plots here, the key to understanding is the numbers. So if you can kind of rearrange this color bar here, that's just a good.
I know what you mean, but then it can zoom in.
I get it,
It's
but
super.
yeah, I get it. I'm reading forward with these, so I don't want to be like on all. So
Yeah, so you prefer like take some of this with this.
exactly. You can kind of zoom in on. Yeah, it's good.
Thank you. Classroom making that.
Everyone's working on their reports.
Shows you another.
Okay.
Also, if you like, you might have confirmation on the room tomorrow.
Okay,
So I'll
good.
probably send you tomorrow a message.
Okay,
I hope hopefully earlier than later.
Yeah.
So you can send an email for next, because like we usually put our meeting for next.
oh, it's set for next Tuesday. Okay,
Because we requested a room.
Yeah.
I'm like, keep it Tuesday or Thursday.
okay. I mean, a little bit later might have been a bit better, just so people have a bit time to kind of plan for it. But Tuesday's okay too. What time are you guys thinking?
It's gonna be like
Okay, I can probably stop by for a bit.
it's 3 to 5 p.m. It's gonna be basically, it's gonna be an info session.
Okay,
Okay. We've run some two things. We're gonna do an info session. People who don't get 100%, they'll find out that we're also gonna have a bowling.
okay,
We rented the bowling alley also for the next, a week later.
okay. Do you want to record the info session just in case people miss it?
I can.
Okay, yeah, that might be good, just because
I'll
that's a
have
little
that.
short notice.
I have to ask for their permission.
Okay.
I'll make sure to get their permission and probably just set up the Zoom.
Yeah.
Record it,
Sounds good.
and I have postings, so one of the things we, actually, last night.
Yeah, let's talk after. Okay, it's 5:30, so let's go ahead and get started. All right, so it's the day that the project's due, so I'm sure that's what most people are doing, working hard on the project. That's why they're not here. How's everyone doing?
Pretty good.
Good, so, yeah, hanging in there. All right, so so I think first thing, I'm gonna address a few questions that I've gotten pretty commonly over the last couple of days about the project, just so I get that information out to everybody. So everyone's kind of on the same page with that. And then from there, we're going to continue on with our direct stiffness. So we have one more example to go over for trusses. And then from there, we're moving on to beams. And so, it's, this section of the class, I think for some people might have just passed by in a flash, just because I think people have just been focused on the project the last couple of weeks. But we're very quickly reaching the end of it. So after we finish with beams, then we're going to be done, and then we're going to get back into ANSYS stuff and kind of get ready for the home stretch of the semester. Okay, And so with that said, there's one announcement that I have to make. So some of you may have noticed it already, but problem set 1 has been posted online. Okay. So problem set 1 is going to be your practice with all the direct stiffness stuff. So it is a long assignment. I kind of hold off on giving it to you just because, I want you guys to focus on the project in October. But now that the project is due today, now you can start working on the problem set. So homework was posted on Canvas. It's all about direct stiffness problems. Okay. And most importantly, is that this is going to be the main problem set that you're going to do, that I'm going to have you do to practice before the midterm exam. Yes. So the midterm exam is going to be an in-class paper exam that's going to take place the last Thursday before Thanksgiving. Okay. All right. So I know the project's due today. I know that's kind of probably what the majority of people are kind of focusing on until 11:59 tonight. But don't ignore that problem set. So make sure you kind of start that because it's a lengthy assignment. So you want to make sure you have enough time to do it. Okay. All right. So that is that's all my announcements. And so are there any questions I can answer about the project or just anything before we start today? Okay. All right. So one thing I want to bring up, and so I think kind of where people are kind of most people are kind of in the stage right now where you guys are done running the simulations and you're kind of drafting up the report. Okay. So one thing I forgot to mention last time, which probably the most common question I've been asked is if you look on the report template, there's a section right after the abstract called the keyword section. Okay. So in a nutshell, the keyword section, what that's about is that it's the template that I gave you was kind of a template for a generic scientific article. So if you're publishing your article in a scientific journal, the main way that people look for scientific journals nowadays is they search for it on, Google Scholar or something like that. And so the keywords are kind of like your Google key search words, right? Question in the chat. So can we have a slightly informal tone to make it fun to read and write? Yeah, of course. And so, it should still be, professional. So, no memes or no, use proper grammar and use proper spelling and everything like that, proper capitalization. But the tone, you can definitely make it a bit informal too. In fact, I would prefer that too. I'm reading 40 of these and then I have to read 40 of your final projects. So it helps, it brings a little joy into my life when you make it a bit informal when you're writing. So for the keyword section for your midterm project, basically you don't have to worry about it. You can omit it if you want. You can delete it from the template, but just you don't have to fill it in. Okay. Another thing I wanted to address, this is probably the most common question I've had just this past week, is the results section. Okay. So the results section of your midterm project, this is where you're going to show me the results of your ANSYS simulation. So your total deformation plots, your equivalent stress plots. Okay. Okay. You want to make sure that your result figures are, they're looking good. Okay. And so, some kind of rules of thumb or some guidelines for this is make sure that your part is properly centered in the screenshot. Okay. Make sure that it's zoomed in adequately well, so it's not just all blank space. Maybe not zoomed in, but let me say it's well framed. make sure you use the screenshot feature on your computer. Don't take pictures on your phone and then include that in there. That's a big no-no for sure. Okay. So make sure your screenshots are looking good. Another important part is that, the way ANSYS displays your results is that it displays it as a heat map. So it shows different colors for different regions. But those colors themselves are meaningless without the legend. Okay. Okay. So make sure that the color legend there is easy for me to kind of read. So I don't have to kind of squint at it or zoom in really far to kind of read that legend. Okay. So make sure your figures look nice, right? So that's kind of the main thing. For some of your ANSYS activities, I've kind of been commenting on that, up to this point, but just to kind of reiterate that. The other thing I'm looking for in the results section is, like I mentioned, I want to make sure that you not only did the simulations, but you really kind of understand and kind of interpret and kind of tell me what's going on. Okay. Okay. So make sure the description of your result is good still. Okay. And so in particular, kind of the baseline that people usually do is that, they put the figure there and they tell me this is the equivalent stress, the maximum stress is this. Okay. And that's it. So, I want to, learn a bit more, right? So, tell me, what, first of all, what is the max stress or what is the max deformation? Okay. Where does it occur? Okay. Does this make sense? And so does it make sense for the maximum stress to be where it is? Not now, Apple. Okay. Does it make sense? Does it make sense relative to the loading that you apply? Does it make sense relative to the objective of your report? Okay. So, when I say that you need to describe your results, there's a lot more that can go into describing your results rather than just saying, the max stress is here, the max deformation is there. Okay. Think about it from the perspective of, someone reading your report that has no idea about finite elements and kind of has no idea what they're looking at, right? And so you kind of need to describe it too, right? And so, I know that's not the case. I'm the one reading your reports and I know ANSYS and I know the part and I know what you're trying to do, but you still have to include all of this. Okay. All right. So I think that's, probably an adequate amount of advice for the last minute. Yeah.
Just had a quick question. Sorry if you went on this. For our, like, figures that we want that they want to add, like, figures, descriptions.
Yes, that would be good. So a brief, it would be good. It's not a requirement, but it definitely helps to kind of organize the report. Yeah.
And so, like, if you have like other figures, if you just are naming them like consecutively.
Exactly. Yeah. Yeah. So you don't have to. So what I've seen people do is that they put the figures kind of in line with the report and they just refer to the figure, just say the figure above. So that's fine. But then if you're going to refer to things like figure 2, figure 3 in different parts of the report, then yeah, labeling each one is cool. Yeah. Mm-hmm. Okay. All right. So that's hopefully that's helpful. And so I did see that some people submitted the report already. So if you submitted your report already, but if you want to make some last minute changes, you can go ahead and submit another one. I'm just going to grade the latest one that's there. Okay. All right. So let's get back to direct stiffness methods. Okay. So we're right in the middle of doing 2D. Excuse me. Oh, sorry. Question in the chat. So if you already turned in the midterm with keywords, should I, no, don't, yeah, if you already turned it in with the keywords, just leave it. Yeah, so the keywords are, if you haven't done it, you can omit it, but if you've done it already, just, yeah, don't worry about it. Okay, so we're right in the middle of doing 2D trusses with direct stiffness. So, after a certain point, these problems start to get a little bit repetitive, I guess. We're just kind of doing the same thing over and over again. But it's one of those things where you kind of have to keep practicing and you have to kind of see a lot of different looks, a lot of different kind of situations, before it really starts to kind of sink in. So I have one more example to do with you before we move on to our next element type, which is beams. And this example here is actually going to is going to bring up a couple new points that we haven't discussed just yet. Okay, so this one's a little bit simpler here. So we have a two element system. Okay, so we have one element that kind of goes slants downward like that. That's going to be element A. And it's connected to another element like that. And this element is going to be connected to a wall via a roller support. Okay? So far, we've only done problems with pin supports, but there's actually more than one type of constraint that we can actually use. So we'll actually kind of see what that looks like here. Okay? All right. So let's look at the lengths. And so the length of this element here, we'll say is 10 feet. Length of this element here is 5 feet. Okay. Second element here is element B. This angle here is 30 degrees. And then let's go ahead and label the node. So let's say the node at the far right here, this is going to be node 1. The node up top here is going to be node 2. And the node here on the roller, that's going to be node 3. All right. We have one load that's being applied here. So let's say we have a vertical load of 25,000 pounds being applied at the end right there. Okay. And then we also need the material properties of the elements. And so let's say that our Young's modulus for each element is going to be 30 times 10 to the 6th psi. And then the cross-sectional area is going to be 1 inch square. Okay. All right. And so just like our previous problems here, we're interested in computing the deformation of our nodes. Okay. And so we're going to compute the deformation of all the nodes using our direct stiffness method. Okay. All right, so our direct stiffness method, so we're going to use the same kind of recipe that we've done before. So element stiffness matrix, assembly, boundary conditions, and then solution in that. Okay, so we're just going to go through all 4 of those steps again. All right, are there any questions on just the setup for the problem here? Okay, good. Okay, so let's start with the element stiffness matrices. Okay, so let's start with element A. Okay, so just like we normally do, let's compute its effective spring constant. So let's compute AE over L. Okay, so remember, that's the factor that's in front of our truss element stiffness matrix. Okay, and so AE over L in this case is, so we take the cross-sectional area, 1 inch squared, multiplied by the Young's modulus, 30 times 10 to the 6th psi. And then we're going to divide by the length. But remember, we need to convert the length into inches. And so that's 10 feet times 12 inches per feet. So that's everything there divided by 120. And so what we get is 2.5 times 10 to the fifth pound per inch. Okay. Okay. Next thing we need to take note here is the node numbers that element A is connected to. Okay. So from this figure here, you can see that element A is connected to node 1 and 2. All right. And then finally, we have the orientation of the element, or the angle. Okay. All right. So this one you have to be a little bit careful because it's very easy to kind of get tricked by the figure here. Okay. So the angle that we're given in the figure is 30 degrees. But that 30 degrees is simply just the angle between elements A and B. Okay. And so I think, the tempting thing I think for most people is that they look at this figure right here and they see 30 degrees. And so they just immediately say that the theta here is 30. Okay. But of course, the reason I'm kind of bringing this up is because it's not actually for 30. Okay. And so you're thinking, how can that be? 30 is the only angle that we see there. Well, let me draw this figure here. And let me just remind you that this theta here is the angle that is used to describe the orientation of this element relative to the positive x-axis. Okay, so let me go ahead and draw the figure here, draw the element again here. Okay, so this is element A. Okay. Node 1 is in the bottom right, node 2 is up top. Okay. And the angle that we're given here is 30 degrees. Okay. Okay, so how can the orientation of this element not be 30 degrees? Well, technically it is. But when we're doing a method like this, we have to be systematic in terms of how we define this angle and what we plug into our element stiffness matrix. Okay? Because whether we plug in 30 degrees or we plug in 150 degrees or maybe 330 degrees, that's going to change the signs of our matrix. It's going to change our results. And so we have to make sure that we're using a consistent methodology for plugging in that angle. Okay. So here's the methodology that I use, or at least kind of what makes sense in my mind. Okay. So to determine the angle for a particular element, what you need to do is you need to identify which node in the element is lower number. And so in this case, our lower numbered node is node 1. So the lower numbered node, okay, that becomes the origin of this element. All right, so that's step 1. So whenever you're determining the orientation for an element, you need to identify which is the lower numbered node. That one becomes your origin. Okay. All right. And so once you've identified the origin, what you're going to do is you're going to draw a positive x-axis originating from that origin. Okay. And so the positive x-axis for node 1 right here is going to go to the right. Okay. And so positive x-axis always goes horizontally to the right of wherever your origin is. Okay. And so from here, what you need to do, so starting from the positive x-axis, what you need to do is you need to rotate counterclockwise until you reach the orientation of the element itself. Okay. So you can think of it as kind of like the hands of a clock, except they're just rotating backwards. Okay. All right, so starting from this positive x-axis, and so if we want to align with element A right here, you can see that we need to sweep out an angle like this, right? So that angle that we kind of rotated counterclockwise from the x-axis to node 2, that there is going to be the angle of our element. So this angle that we're sweeping out, this is what we plug into our element stiffness matrix. Okay. And so you can see from this figure right here, so you can use a little bit of geometry to obtain it. And so that theta there is actually going to be 150 degrees. Because we almost do a full half rotation here. So we almost go 180 degrees, but we stop up to 30 degrees. And so the way that we obtain that angle there is we take 180 degrees and we subtract 30. And so that's how we get 150. Okay. So for this particular element, our theta that we're going to plug in is 150 degrees. Okay. All right, so this is probably the biggest point of confusion for this section here is, how do you compute your angles there? So up to this point, the previous examples that we did, the angles were pretty straightforward. I made sure to draw it so that, the angle was always in that first quadrant of the Cartesian plane. But now that, we're getting to more complex problems, you may have to plug in some interesting values for the angles here. And that's going to change our results. So that's going to change the signs of our sine and cosine terms. All right, any questions on how we determine these angles here? Okay. All right, so with our angle at 150, let's go ahead and compute sine and cosine. Okay, so C here is cosine of 150 degrees. Right, so you punch that into a calculator, we see that this is equal to minus √3 over 2. And then S is equal to sine of 150 degrees. And so this is equal to a positive 1/2. Okay. All right, so let's take all these results and let's compute our element stiffness matrix for element A. Okay, so our element stiffness matrix for element A, first we have our factor out in front, which is 2.5 times 10 to the 5th. Okay, remember that was our AE over L factor. Okay. And then we have combinations of cosines and sines, cosine squares, sine squared, cosine sine. And so we do all that, we get 3/4 minus √3 over 4 minus 3/4 and √3 over 4. Okay. We have to connect this to the nodes of that element. We have d1x, d1y, d2x, d2y. All right. So let's take advantage of our symmetric matrix again. So let's take that first row and then write it into the first column. So second row here is going to be minus √3 over 4. Third row is minus 3/4. And then last row there is √3 over 4. Okay, so let's go second row. So second row, we have a 1/4 on the diagonal. We have a √3 over 4, and then a minus 1/4. Okay, and I'm gonna take that row and then write it into the column. All right, so third row, we have a 3/4 and then a minus root 3 over 4. I'm gonna write that into the column, so that's gonna be a minus root 3 over 4. And then the last entry in the bottom right is just gonna be a positive 1/4. All right, so things are a little bit more complicated when your angles are not 0, 45, or 90. So you have a lot of radicals here. Okay. By the way, for the homeworks and the exams and everything like that, I'm never gonna give you something weird like 27 degrees. It's always gonna be some multiple of, 0, maybe 30 degrees, 45, 60, 90, and then, everything that's kind of beyond that as well. So no, there's no weird numbers here. So if you're really fast with your trig computations, then that's going to help you a lot in this section. All right, any questions on how we obtain this element stiffness matrix here? Okay. All right, so let's go with the element B now. So element B, first let's compute AE over L. Okay. So the Young's modulus and the cross-sectional area for element B is the same as element A. The only difference is that the length is half. And so it's going to have a different value here. So this is going to be 5 times 10 to the 5th pounds per inch. Okay. Next, we have the nodes that is connected to. So the nodes that is connected to is nodes 1 and 3. Okay. And then we come up to the angle. So this one you have to be a little bit careful as well, although in the end, it's not going to make a difference whether you use 0 or 180. But let's be precise. Let's kind of put our new our new theory into practice here. Okay, so I'm gonna go ahead. I redrew the element here. It's a horizontal element, so that's good news. Okay. So once again, I'm gonna go to the lower numbered node here. So the lower numbered node is 1, and I'm gonna make that my origin. Okay. And so from the origin here, I'm gonna draw my positive x-axis. Okay. And then from there, I'm going to rotate counterclockwise from the positive x-axis until we are aligned with our element. Okay. So in this case, we have to rotate 180 degrees. Okay. So we do a half rotation there. And so this tells us that our theta is 180. Okay. And so we take cosine of 180. Cosine of 180 is -1. And then sine of 180 degrees is 0. Okay. Okay. So in this case, even though we get a -1 instead of +1, it doesn't end up making a difference just because of how, you end up just multiplying cosine squared anyway, and then anything multiplied by sine is just going to be 0. So, we still end up with the same element stiffness matrix as if it were theta is equal to 0, but, I wanted to kind of illustrate to you kind of, how I obtain that angle. Okay, so let's go ahead and write our element stiffness matrix now. All right, this is KB, excuse me. So KB here is going to be 5 times 10 to the 5th. We have our matrix here. So first row of the matrix is going to be 1, 0, -1, 0. Okay. We have D1x, D1y, D2x, D2y. Okay. I'm going to write this into the first column. Okay, so we have 1, 0, -1, 0 in the first row, and then 1, 0, -1, 0 in the first column. Second row has all terms with sign, and so that's going to be all zeros there. It's the same thing. The entire second column is going to be all zeros. All right, third row. Third row, we start out with a 1 and then a 0. Okay, we write that 0 down as the bottom column as well. And then in the bottom right term is sine squared, so we end up with the 0. All right. So element B, a little bit simpler. We have a lot more zeros and some ones. All right. So now that we're done with our element stiffness matrices, the next step is assembly. So we only have two elements here. So we only have two matrices to assemble. And in fact, we only have 3 nodes. So our matrix, our total global matrix here is only going to be 6 by 6. All right. All right, so I'm going to make a matrix here with 6 columns. And so our 6 columns here are going to denote the x and y components of all the nodes. We have d1x, d1y, d2x, d2y, d3x, d3y. And then we have d1x, d1y, d2x, d2y, d3x, d3y. And all this is equal to the right-hand side forcing vector, which is f1x, f1y, f2x, f2y, f3x, f3y. Okay, so once again, just like we always do, let's first box out the areas of the matrix here that we're going to plug in. Okay. So let's do element A first. Okay. So we know element A is connected to nodes 1 and 2. So let's factor out those areas. Okay. So that's going to be the first 4 rows and first 4 columns. Did one nice contiguous block there, so that's kind of nice. And then element B, is going to be nodes 1 and 3. Okay. So everything that's associated with nodes 1 and 3. So that's the first 2 columns, first 2 rows, first 2 columns, 5th and 6th row. Okay. So actually, let me just box these as I'm talking. Okay. And then we have these 2 over here. Okay. So that's the first 2 rows and the last 2 columns. Okay. Then we have the last 2 rows and the first 2 columns. Okay. Then we have the last 2 rows and the last 2 columns. Okay. Okay. And so from here, you know the drill. And so we're just going to plug into our matrix here. Okay. First of all, let me go ahead and put our factor out in front. So this one's a little bit harder to determine just because, we have some irrational numbers there. So the only thing I'm going to put out in front there is going to be just the 10 to the 5th factor. just so that everything else in the matrix here is going to be all in decimals. Okay, so let's start with element A. This one's actually very annoying. Okay, so element A here, in the top left, we have a 1.875. It's going to be very annoying with all the root 3's in there. Okay. So remember, the way I'm obtaining these is that I'm going back to element A right here. I'm taking 2.5 times 10 to the 5th, and then multiplying them through each term in the matrix there. Okay. All right, next we have minus 1.08. Then we have minus 1.875, positive 1.08. Then we have a minus 1.08, 0.625, 1.08, minus 0.65, minus 1.875, 1.08, 1.875, minus 1.08, 1.08, minus 0.625, minus 1.08, and then 0.625. It gets messy when you have you know, root 3's floating. I won't do these too often to you. So most of the time, you know, the problems I'm going to give you are going to be either, you know, 0 degrees, 9 degrees, or 45 degrees, and then, you know, and then the multiples of those things. Okay. All right. So that's element A. Thankfully, element B is a lot easier just because it's, you know, first of all, there's only 4 non-zero values. And it's a nice whole number. Okay. And so first thing that we have is we have a plus 5 times 10 to the 5th up in the top left. Okay. Everything else there is 0. So for everything else that's 0, I'm just not going to do anything for those. Okay. And then for out here, we have a minus 5, 0, 0, 0, minus 5, 0, 0, 0, and then positive 5, 0, 0, 0. Okay. All right. Last thing I'm going to do here is I'm going to fill in all the empty space with zeros, right? So we have some parts of this matrix that aren't filled. And so everything that's not filled, I'm just going to put a 0 for this. All right. So that's our global matrix. And so we have our 6 equations and 6 unknowns. You know, we're ready to apply boundary conditions. All right. Any questions on how we got to this point here? Okay, good. Okay, so next thing, we're going to apply our boundary conditions. Okay. In other words, we're going to take a lot of the hard work that we just did right here and just erase it. So that's always a good feeling. Okay. All right, so the first one that I'm going to apply here is probably the most obvious one. Right, so let me scroll back up to the figure here. And so the first boundary condition that I'm going to apply is a fixed support on node 2. Or I should say it's more like a pin support. Okay. So pin support we've seen already before. And so a pin support has the ability of basically constraining both components of the deformation. So it constrains both the X deformation and the Y deformations. Okay. So what this means is that both deformations on node 2, so that's D2X and D2Y, are going to equal to 0. Okay. So that means that we're going to apply the what we usually do for constraint type boundary conditions on the third row and the fourth row of the matrix. Okay. Okay. So third row in the matrix is going to be this one right here. And then fourth row in the matrix is going to be this one right here. Okay. So let's apply what we usually do. So let's go ahead and zero out this entire row, except for the entry on the diagonal. We're going to put a 1 there. Okay. We're going to erase all this. Okay. Those ones are already 0, so I'm just going to leave those alone. And then we're going to turn the right-hand side equal to 0. Okay. So this can become 0, 0, 1, 0, 0, 0, and then 0 out there. Okay. And then we do, now we need to do the fourth row. Okay, so same thing. So I'm going to erase all the non-zero values. Okay. I'm going to erase F2Y as well. Okay. And I'm going to plug in 0s and 1s into the matrix. Okay, so that's pretty straightforward there. So not much doing on that. Okay. Now let's go with our next support. So our next support, we have a special kind of support on node 3. Okay. So we haven't seen these in a problem yet. So node 3 has what's called a roller support. Okay. So you've probably seen roller supports, in your previous classes, probably in your statics class, to some degree. Okay. So what's unique about the roller support is that it only constrains one dimension of the deformation. Okay. So whereas a pin support constrains both the X and Y, the roller support is only going to constrain one of them. And which component of the deformation that it constrains depends on the direction of the roller support itself, right? So if we go back up to the figure here, we can see that the wheels on this roller support are on a vertical wall, okay? Right? And so what we can assume here, what we can see just from based on the direction of the wall and direction of the way the wheels are facing, is that the Y component of deformation here is going to remain unchanged. So D3Y here is free. Okay. D3X is going to be constrained, right? So D3X is constrained by the roller, because we always say that this beam, this truss cannot extend into the wall. And kind of the implication or the assumption with the roller supports is that it prevents pulling out as well. And so there's no way for D2X to be non-zero. Okay. So D3X is constrained to be 0. Okay. All right, so that means, so what does this mean for our matrix? And so what this means is that, we're only going to apply the constraint on the D3X row, but we're going to leave the D3Y row alone. Okay. So let's go back to our matrix. Okay. So we're looking at the two rows for D3X and D3Y. We know that D3X is going to be constrained, and so I'm going to go ahead and circle that. Let's go ahead and apply our constraint. So once again, we're going to zero out everything in that row except for the diagonal entry. Okay. So that fifth row in the matrix is going to become 0, 0, 0, 0, 1, 0. And then we have a 0 on the right-hand side vector. Okay. The fourth row we're just going to leave alone. Okay. And in fact, actually, what we can say is that the Y component there is unconstrained and there's no force being applied on there as well. And so we can just go ahead and replace F3Y with a 0. Okay. But other than that, we leave the rest of that row alone. All right, any questions on the roller support here? Okay, good. All right, so this idea of having supports that only constrain one dimension of the of the solution is going to be important, once we get into beams as well. All right, so the last load that we have, or the last boundary condition that we have to apply here is the load. Okay, and so we have a load of 25,000 pounds. Okay, and this load is being applied on node 1 in the negative y direction. Okay, and so that means that F1y is going to be equal to minus 25,000. Okay, so let's go ahead and fill that in here. And so F1y, I'm going to replace that with minus 25,000. And then we have no force in the x direction, so I'm just going to go ahead and change that to 0 right there. Okay. All right, so that's all of our boundary conditions applied on our matrix here. All right, so normally at this point, after you apply the boundary conditions, this is the part where you start to solve it in math. Okay. There's one problem with this particular matrix though. And so if you notice, if you look at the last row in the matrix, and actually the last column as well, right? Actually, let me use a highlighter for this. Let's use red. Okay. So if you look at this last row in the matrix and this column right here, so that's kind of ugly. Okay. We'll just look at the last row, and we'll say the last column looks exactly the same. You'll see that the entire row there is 0. Okay. So that's really interesting. And so, we've never had this before. So we've never had a row of entirely zeros. So what does this mean? So when you try to actually solve this in MATLAB, what MATLAB is going to tell you is that, this matrix is ill conditioned, or that's if it's feeling nice to you. If it's normal MATLAB, is that this sucks. I'm not doing this. Okay. So when you have a matrix or when you have a row of all zeros and you try to solve a system of linear equations with it, you're basically unable to do so because a row of all zeros basically means that you don't have that equation there just doesn't exist. Okay. So last row is all zeros. Okay. And so basically, we're working with kind of one less equation right here. So we have basically 5 legitimate equations. And so 5 equations with non-zero values, but then our 6th equation is just a no-show because it's all zeros there. Okay. And so what this means is that our system here is actually under constraint. Okay. So we can't actually solve the system because there's no actual equilibrium position that can be achieved with these constraints. Okay. All right. So when you encounter this in your problems, and it's not uncommon to do so, you need to add more constraints to the problem in order to get a solution. Okay? And so the problem itself, this tells you that the problem itself was flawed, and that you need it, and so more constraints are actually needed in the problem to get a proper solution. So we can solve this system if we add more additional constraints, right? So what's the issue here, right? So the main issue is that, this node 3 is under constraint, right? What was node 3? Node 3 was our node with the roller support, okay? So the fact that we get a matrix of all zeros there means that this roller support is insufficient in constraining this system. And so in order to actually solve it, we need to convert that roller support actually to a pin support. Okay. Okay. And so if we convert that last roller support to a pin support, then that will allow us to put a 1 on the diagonal entry of the last row. And so that'll give us our last equation. Okay. So, was it a waste of time for us to go through the roller? You could make that argument, sure. But, this idea of a roller support is going to come back, once we talk about beams. And so I wanted to introduce the idea here. It ended up not working out. We ended up needing more constraints. But this idea of having constraints that, only zero out or only constrain one dimension is going to be, relevant moving forward. Okay. And so this problem here, is probably familiar to some of you in ANSYS, and some of you have probably run into this. So if you run into the error in ANSYS called the solver pivot warning, that's exactly what's going on here. Okay. So hopefully that gives a little bit more context in terms of, what ANSYS is actually saying, right? So a solver pivot warning basically means that, you have, ANSYS generated a matrix from your system. It applied the boundary conditions, but it wasn't able to solve the system because it wasn't able to pivot around a row of all zeros. Okay, so it's a numerical issue that's born from the fact that you don't have enough constraints. Okay, either you don't have enough constraints, or I think more commonly, a lot of you kind of found this error in activity 4. The connections between your parts wasn't properly set, and so you ended up with matrices that were, or you end up with a structure that was under constraint, and there were just not enough equations there to solve for the unknowns. Okay. So that's what that means. And so, solver pivot warning usually means that you don't have enough constraints in your system, or maybe the connections between the parts in your assembly are not well defined, or maybe they're just not close enough. And so you need to kind of examine those things within ANSYS. All right, any questions on that? Okay, all right, so we have about 20 more minutes. I could start the beam stuff, but I think probably it'd be better to start it when more people are here. So let's call it here today. I'll stick around for the next 20 minutes. If you have kind of last minute questions on your project, I'll go around and kind of answer those. But if not, if you've already kind of submitted your project, or if you're just making final touches, or you don't have any final questions, then we can go ahead and call it here. So thank you guys for coming today. Have mercy on us for the exam. Yes. So last, some people may have heard. So last year I gave the exam for this class. It was very long and very difficult. So I'm very aware of that. And so, I'm definitely going to make it more reasonable this time. So, yeah. So it's I'm aware. So yeah, the exam will be more doable this year than last year. It'll be shorter. That's the main thing. All right, so thank you guys for coming today. Best of luck on your final projects. I do have plans this evening. I'm probably going to be leaving my office at around 7:30. And so if you have last minute questions, try to get it to me before 7:30, just so I can answer your emails. If not, then just make sure you get your project in on time by midnight, and I'll have those graded for you by next week. So thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you next Tuesday.
I like this, just to clarify, up here, like, this is the first that they were completely. Just specified.
Yeah, no, that definitely helps a lot. Oh, yeah, no, that's.
Okay, then I can see it. Introduction. Sometimes they need, sometimes relevant something about it. One thing I do have is like the eight, this one, I think I on one side it was all red, but the other side has this orange. Okay. That's what I'm talking about. Yeah. No, that's good. Yeah.